All right, we're recording now. Welcome back to Cohomology, everyone. Does anyone have any questions about what we talked about recently or anything else in the course? All right, if not, let me just briefly remind you where we were. So last time we computed the Étale cohomology of a curve, finally. So that was what we were working up to for most of this time. So today I want to start talking about compactly supported cohomology. And cohomology and Gaussian sequences. And so the philosophy I have in mind for this part of the course until we get up to actually proving stuff about the Weil conjectures is I want to focus on the kind of computational aspects of Étale cohomology, like how can you actually compute the cohomology of a variety? And at some point we're going to have to use some big theorems soon. So we're going to have to use, in particular, probably by the end of today or the beginning of next time, I'll state the proper base change theorem, and I've decided I'm not going to prove it. I think it would take too long. It would basically take the next 2 or 3 weeks to develop everything we would need, and then we would not get to any of the cool stuff about the Weil conjectures later. So if you're interested, we can talk about it. I'll try to give you some idea about the proof in class, but I'm probably not going to prove that, and there are a couple other big theorems that I'm not going to prove. I'll only state and then use as black boxes. All right, so with that, let me remind you what we did. So we computed the Étale cohomology of curves, and we said basically that the cohomology looks like the cohomology of a topological surface. So in degree 1, it's z mod L to the nz. In degree 2, it's, if you have a smooth proper curve, it's z mod L to the nz to the 2g. And in degree 2, it's z mod L to the nz again, although up to, and this is a non-Galois covariant description. So now I want to start talking about open varieties. And in order to do that, we're going to have compactly supported cohomology, as I wrote above. And so I want to introduce a notion called extension by zero in order to define what that means. So maybe some of you have seen this before, but I just want to remind you. So suppose I have an open embedding u into x. So here this is an open embedding. So we already have one way of going from sheaves on u to sheaves on x, and I want to describe another way. So here's the definition of extension by zero. So this is a functor, J lower shriek, from sheaves of abelian groups on U to sheaves of abelian groups on X. And what it is well, you just extend by zero. So what does that mean? So J lower shriek, that's how you pronounce this, of V, where V is some Étale morphism to X, is going to be it's going to be F of V crossover X with U if the image of V inside of X is contained in U, and zero otherwise. All right, so for example, when you evaluate J lower shriek of F on U, you just get it's the global sections on U, but as long as U is not all of X, when you evaluate it on X, you just get zero. All right, are there any questions about this definition?
Is it a pre-sheaf or already?
Sorry, you're absolutely right. So this is just a sheafify. This is just a pre-sheaf, yeah, and then you have to sheafify it, yeah. So here A denotes the sheafification. So this is actually just a strict pre-sheaf. Thank you so much for that correction. I'm still drinking my coffee today.
You see what the superscript above the U is? It's the,
I'm sorry?
the superscript above the U. Like image of J
Where is there a superscript above the U?
image of V is contained inside X. Is
Oh,
contained
that's just another contained in.
I see. Okay.
Yeah, so it says the image of V and X is actually contained in U. So V is a map to X, its image is some open, and I would like that open to be contained in U. Does that answer your question, Arvind?
Yeah. Thanks.
Okay, great. All right. So some basic properties. Let's discuss this.
Excuse me.
Yeah, go ahead.
So you only define this for Zariski open embeddings,
Nope.
not for net
Oh, you mean for J lower streak?
Yes.
I've only defined for U as Zariski open. Yeah, that's correct.
Okay.
Yeah, I'll define it in more generality later, but it's highly non-trivial. Yeah, so that's a good question. Yeah, so yeah, that's actually a really good remark. Remark. Some kind of J lower shriek exists for more general morphisms. And we'll see it later. But it requires real input. So it requires input from Nagata compactification, and I'll discuss that if you haven't seen that before. All right. So what are we trying to do here? So we're trying to understand a notion of compactly supported sections. That's what we're working towards. And so this is going to be if you have an open variety, so a non-proper variety, one way to think about compactly supported sections on it is you can how should I say this? Yeah, so in topology, the compactly supported cohomology has two descriptions. So one, if you have a sheaf, you can just take its sections with compact support directly, and then take the derived functors of that. And the other way in topology to define compactly supported cohomology is to compactify your space, extend the constant sheaf by 0, and then take the usual cohomology of that. And so it turns out that only one of those techniques works in algebraic geometry, and that's the motivation for this definition. Okay, so let me tell you some basic facts about this functor. And so the first one I'm going to leave as an exercise, but I'll prove a few things. So the exercise is that this J lower shriek functor is left adjoint to J upper star. All right, and the proof is an exercise, but I'll just say a word about it. So the proof is to check this on pre-sheaves and use the adjoint property of sheafification. And to check on pre-sheaves, you just check directly using the definition. Great. All right. So what does this J lower shriek look like? So let's compute its stalks. So let's suppose we have J lower shriek of some sheaf F, and let's take the stalk at some geometric point X bar. So can anyone tell me what this is? Let's just compute it. So what is the stalk at a geometric point X bar? So there are two possibilities, right? Either X bar is in the image of J, or X bar is not in the image of J. So does anyone want to take one of these? So what happens if our geometric point is in the image of J? So namely, it's in this open we started with. So what are we doing when we take the stalk? We're taking an inverse limit over small Étale opens. And if X bar is in the image of J, those small Étale opens are going to map into U. So what do we get?
Like the usual strict Hanselization?
Well, here we're just starting with some arbitrary sheaf F. So you're right, we'd get that if we started with O. But with an arbitrary sheaf F, what do we get?
Like the usual stock?
Yeah, exactly. We just get Fx bar. All right, now what if X bar is not in the image of J, meaning any open containing it is not contained in U, or any Étale thing, any pointed Étale map, mapping to any Étale neighborhood of X bar is not in the image of U. What do we get?
0.
Ben, I see your square is lighted up.
0?
Yeah, exactly right. So we're just taking an inverse limit of literally everything in the inverse limit is 0. So we get 0. Okay, so stalks were kind of easy. So we actually just proved this theorem, this proposition.
Sorry, it's a direct limit, right?
Oh, sorry, you're right, direct limit. We're taking a direct limit of zeros. You're exactly right, Arvind. Thank you. So a corollary is that J lower shriek, this functor, is exact. So can anyone prove that for me? So how do you check a functor is exact?
So check on stocks and you.
Yeah, exactly. You check on stock. So suppose you had an exact sequence of sheaves on U. You take their extension by 0 to X, and well, the stocks are the same on U, so those are exact. So they're exact on U, and away from U, they're just 0, and the sequence 0 to 0 to 0 is exact. So we've shown that this is exact. Great. All right. So what is this useful for? So already, I think it's not so hard to see that this is useful for computing the cohomology of an open in terms of a compactification and its complement. And let's see why that is. So this is useful for what I'll call excision. And we'll see fancier versions of excision in a little bit, but this is sort of the prototype, which is a way of relating the cohomology of a sheaf on an open to something on a complement and on a compactification. So here's the proposition. So suppose we have F in sheaves on X, Étale. These are abelian sheaves. And then we have, as before, we have an inclusion J into X and an inclusion of Z, which is X minus U. So this is open and this is closed. So here we've been open of X and its complement. Then there's a short exact sequence where we take our sheaf F, we pull it back to U, and we extend by 0 first. This I claim is going to map to F, and we'll see that map in a second. And then I claim the co-kernel is I lower star of I upper star of F. So we pull back to Z, and then sorry, this map is I, and then push forward again. So the claim is that there's a sequence like this which is exact. So let's first see what are these maps. So can anyone tell me what is the map from J lower shriek to J upper star F to F? Or how you would make it? Well, I can see two ways to make it. So first of all, we had this exercise earlier, which proposition, which I leave to you as an exercise, that J lower shriek is left adjoint to J upper star. So this is the unit or co-unit, whichever one it is of that adjunction. So in other words, it's what you get by applying adjointness to the identity map from J upper star F to J upper star F. There's a more prosaic description, which is this pre-sheaf we used when we defined J lower shriek evidently maps to F. Namely, we just send a section to this thing to the appropriate section, and then you use the left adjointness property of sheafification to make this a map out of the sheaf. All right. What about this map from F to I lower star, I upper star F? Can anyone tell me how to do that one? Any thoughts? So my hint is that I already said the correct sequence of words when I was over here.
Does the lower star be the right adjoint of the upper star?
Yeah, exactly. So the existence of this map follows from the adjointness of lower star and upper star. Great. And you could also define it more prosaically. I mean, where does it come from? It comes from taking a section to F and restrict it to I upper star of F. Great. So we've made these maps now. So now let's prove exactness. So can anyone give me a hint as to how to prove exactness? So how do we check exactness?
Check on stocks again.
Yeah, exactly. Let's check on stocks. So let's check on stocks and what happens. So let's choose a geometric point. So choose X bar in X, a geometric point. And there are two possibilities. So case one is that X bar is in U. And case two is that X bar is in Z. So what happens if X bar is in U? Can anyone tell me? So what does this sequence become when we go to stocks? So
it's just identity and then 0.
Yeah, so we just get the identity on fx bar. And this I lower star, I upper star F is just supported on Z. If you pull it back to U, you get 0 just by definition. So we get this sequence, that's certainly exact. What about if X bar is in Z, what happens?
A 0 on the first component.
Yeah, exactly, you get 0 to fx bar to the identity to fx bar to 0. Great, that's the proof. Okay, and you should check for yourself that the maps we've gotten here actually agree with the maps that we constructed, for example, via adjointness or using a concrete description. Okay, so we can now give a definition of cohomology with compact support using this. So this is the definition of cohomology with compact support. So suppose F is an abelian sheaf on U. And as usual, suppose we have an open embedding U into X, open. And let's assume furthermore with X is proper. Then, and this is only a pseudo definition right now, and I'll say what I mean by that in a second. The cohomology of U, the coefficients in F, compactly supported, so this C here denotes compactly supported cohomology, is defined to be the cohomology of X with coefficients in J lower shriek of F. Okay, and there's some natural questions here. So one, why does such an X exist? Like, can you always put something inside of a proper variety? And the answer is no in general. I mean, and we'll see why in a second. And two is, why is this definition independent of this embedding J into this proper variety X. Okay, and that's highly non-trivial, so that's going to require proper base change, which we'll get to later. But that said, are there any questions about the definition given an embedding U into X? Like, so right now we can think of this as a definition which is relative to such a choice. So are there any questions about this?
So the term on the right-hand side, that's you take like the Étale sheaf associated to J shriek of F.
Yeah, J shriek of F is an Étale sheaf on X. That's part of the definition is that it is such an object. And then we can take the cohomology of that thing. That's exactly right.
Oh, so the original F was an Étale sheaf. Then.
Oh yeah, sorry. This is U Étale. Sorry about that. Yeah, that's right. Does that clear things up?
Yeah, thanks.
Great. Yeah. Okay. So let me just briefly kind of remind you what this is supposed to be analogous to, if you haven't thought about compactly supported cohomology and topology. So there's a few ways of defining it. Maybe the simplest one, in my opinion, is if you have a manifold, you can take the complex of compactly supported C infinity differential forms. So those are just C infinity, like things that locally look like F times dxi wedge dxj wedge blah blah blah, where F is a smooth function, and moreover F you ask that these be compactly supported, meaning that they're the place where there's a compact subset of the manifold, so that where they're non-zero is contained in that compact subset. So that's a chain complex, and if you take the cohomology of the global sections of that chain complex, you get something called compactly supported Jurand cohomology. Okay, so what's the idea of this compactification? Well, suppose you have an open manifold, and if you have a compactly supported form on that thing, well, if you embed it in any other manifold and extend by zero, you get a compactly supported form. All right. Now on a compact manifold, everything is compactly supported. So one way you can compute these things is you choose a compactification of your manifold if such a thing exists, and then just extend all the forms on your manifold by zero, and then compute on this compact thing. And so that's what this is trying to capture, except with sort of a general sheaf, not anything related to differential forms. At least that's how I think about it. Are there any questions about that?
Yeah, I have one question about why does it independent of the choice? So you mentioned that you should use a proper base change, and I think in the theorem we have to require the sheaf to be torsion sheaf, right?
Yeah. So we're only gonna check that for torsion sheaves. That's right.
Right. So I think for this cohomology compact supported, we should focus on the torsion sheaf, or
yeah, as far as I know, it's I don't actually know a counterexample, but as far as I know, it's only proven for torsion sheaves to be independent of the compactification.
All right. Thanks.
Yeah, that's a good point. So I'll state that more rigorously later on. Yeah, that's.
If you were going to give some examples, I was wondering about some simple examples like a curve minus a point or such things like that.
Oh yeah, I'm about to do that. And once I want to discuss a little bit about these questions, and then we'll do curves. Yeah, that's a great that's a great question. Yeah. So first of all, let me just say a little bit about the existence of these compactifications. Okay, so there's an obvious obstruction to the existence of such a thing. Can anyone give me an example of a scheme with no proper, which is not an open inside of a proper scheme?
Should you be separated? Is this what you're looking for, Daniel?
Yeah, that's right. So proper schemes are always separated. So if U isn't separated, then there's no way to embed it in a proper scheme. That's exactly right. Okay, so that said, there's a theorem of Nagata which says this is the only thing that can go wrong. So the theorem is that if you have U to S, which is a separated map, so above we're in the situation where S is a point, so we just have a separated scheme, and then the theorem is that there exists an embedding of U into some X where this is open, and this map X to S is proper. Okay. So this is the statement, and okay. So applying this when S is a point, if U is separated, we can always find a compactification. So for us, we're always going to be thinking basically about quasi-projective varieties, and then you can just take the closure in projective space, and that's a perfectly good compactification. Okay, and then for 2, I've already said this. So the independence, and this is as Peter asked, this is for torsion sheaves. Will require proper base change.
What if you take something that's not finite type over S?
I think this is okay. You're asking about Nagata compactification?
Right, because then how does X become finite type?
Oh, sorry, you're saying, yeah. Sorry, I think what's true is that you can find a universally closed thing in general, but you're right. If you want X to be actually proper, then you need to be finite.
Okay, that makes
That's
sense.
right. Yeah, sorry about that. Okay. All right, so let's talk about curves. So this is a proposition / example, I guess. So let's suppose that U is a connected regular curve over an algebraically closed field, but not necessarily proper. And let's suppose that N does not, that the characteristic of K does not divide an integer N. Then what we want to do is we're going to compute the Étale cohomology, the compactly supported cohomology of U. So in particular, the proposition I want to state is that there's a canonical isomorphism H2 compactly supported of U Étale with coefficients in mu n with z mod n z. So just like in the proper case, but in the proof, we're actually going to more or less compute the Étale cohomology of this curve, or the compactly supported cohomology of this curve. All right. So and again, I mean this presumes good properties of compactly supported cohomology, like independence of compactification. But for a curve, there's a canonical compactification, so this isn't too scary. Are there any questions before I start talking about the proof? All right, so U lives inside of curve X, so this is the canonical regular compactification. And we want to compute, so we want to compute hi of X with coefficients in J lower shriek mu n. So can anyone suggest how one might go about this?
Use the exact sequence?
Yeah, so let's use the exact sequence. So we get an exact sequence, 0, so J lower shriek, J upper star, mu n to I lower star, I upper star, mu n to 0. Where here I is the inclusion of z, which is x minus u into x. So that's just a disjoint union of finitely many points. Okay, so can anyone help me identify these sheaves? So what is J lower shriek of J upper star mu n? Well, what's J upper star mu n, I guess is my question first. So this has a slightly more concrete description. So I claim J upper star mu n is just mu n. Can anyone tell me why that is?
It's the restriction for an open subset. So
Yeah, exactly. So if you just think about what the functor is, well, you just evaluate on an open subset, and that maps into mu n. And that's, yeah. So this we can also write as just J lower shriek of mu n. And what do we know about this I lower star, I upper star mu n?
It's supported on a point.
Yeah, on some collection of points. So this is a direct sum of skyscraper sheaves. All right, so what do we get? We get a long exact sequence. H. Let's write it this way. So we get a long exact sequence HI of compactly supported cohomology of U with coefficients in mu n. That's the cohomology of this first object to HI x mu n to HI x I lower star, I upper star mu n. We'll describe this in a second. This goes to HI plus 1, compactly supported U with coefficients in mu n. Okay, so this is the long exact sequence suited to this short exact sequence of sheaves. All right, this we've computed, this object here. Can anyone tell me how to compute this object? Any thoughts?
It's a skyscraper sheaf, so.
Can you say more? Yeah, so how do you compute the cohomology of a skyscraper sheaf? Yeah, let's actually work it out here. So we have HI of x with coefficients in I lower star, I upper star mu n. So what is this cohomology? So, and here it's key that we're working over an algebraically closed field.
Is it like Z mod n if it's 0?
Yeah, so it's a direct sum of copies of mu n of k. Well, that's just mu n for I equals 0, where this is the number of points. And it's 0 for I bigger than 0. Can you say how you see that?
So 0, it has to be global sections.
Yeah, so for 0, it's global sections. So you have a direct sum of skyscraper sheaves, great.
And I was just thinking for H1, at least you can argue that there's no like non-trivial extensions.
Yeah, so the way I would say it is there's a Leray spectral sequence, which goes from HI of x with coefficients in Rj, I lower star, I upper star mu n. And this goes to HI plus j of this finite set of points with coefficients in mu n. All right, and this right-hand side is what we actually put down over here. This is this thing. So what we need to do is understand the left-hand side, and the claim is that Rj, I lower star of I upper star mu n equals 0 for j bigger than 0. Why is that?
The map is finite.
Yeah, exactly. So I lower star is exact. As it's pushed forward along a finite map, which we showed was exact a few class periods ago. Great. Yeah, so this is the kind of argument that one needs. Okay, so that lets us work out what this, we now have this fairly explicit sequence. So we now know what these terms are. Those are the cohomology of a curve, which we've worked out. And we know what these terms are. They're just in degree 0. They're just a bunch of copies from UN, and in degree bigger than 0, they're just 0. Okay, so let's actually write out the sequence. So we get 0 to H0 compactly supported U, mu n. So let's assume that mu is actually not just equal to x. So what is this in this setting? What if U is actually an honest open subset of X? So what is this? Let me remind you, this is H0 of X with coefficients in J lower shriek of mu n. And so if U is not equal to X, we can just evaluate this from the definition. What's the answer? So how do you evaluate J lower shriek on a set that's not contained in U?
It's probably
Then it's
0.
simple.
We have to sheafify.
Yeah, it's just 0. Yeah, so if you think about what happens when you sheafify, you're just taking stuff which is forced to be 0 on a big open, and yeah, and mu n is locally constant, so that means it's 0. That's right. And we'll also see that from the long set sequence we're about to write down. So then we have H0 of X mu n. That's just mu n. Sorry, let me write it mu n of k, just so I'm not abusing notation. So that's just roots of unity. Then this maps to this direct sum of copies of mu n of k. So this is the direct sum of the number of points in the complement. And this map is just the diagonal embedding. Then we have H1 compactly supported of U into, which is what we're interested in. Well, one of the things we're interested in, that maps to H1 compactly supported of X. So this is the n torsion in pick 1, or sorry, n torsion in pick. Then this maps to 0. So that's H1 of the skyscraper sheaf. Then this maps to H2 compactly supported of U, which maps to H2 of X mu n. And then this maps to 0, and the rest of it is 0. Okay, and this we showed last time was just Z mod NZ. So we've now shown, we've proven the theorem. So we've shown this is Z mod NZ, because it's isomorphic to this group. And I think Bob asked, what is compactly supported cohomology of U in degree 1? Well, now we can say the answer. It's an extension of the n torsion and pick of the compactification, which is, well, as an abstract group, Z mod NZ to the 2G, by well, we're taking a bunch of copies of mu n, one for each point we've deleted, and modding out by the diagonal mu n. So it's an extension of the n torsion pick n by mu n to the m minus 1, where m is the number of deleted points. And that's what you would expect, I think, from the complex situation. Like that's exactly the same as the cohomology of a punctured Riemann surface. Are there any questions about that?
Can you quickly explain why the first H0 is 0?
Yeah. So this is if U is not equal to X, and so it's morally what you're saying is you have a non-compact variety, and you want to know what are the compactly supported sections.
Oh, but they're all supported on some kind of open. So
yeah. So here, what are we saying? We've extended mu n by 0 to X, and then we're evaluating on X. And the definition, if you remember, at least of the pre-sheaf, there's a little issue with sheafification that you have to think about, which is the definition was that if you evaluate on an open not contained in U, and X is not contained in U, then you just get 0.
oh, okay, cool.
Yeah, that's a good question. I mean, in fact, what's true is that this, how should I say this? This J lower shriek of mu n is actually representable, and the representing object is you just take a copy of X, and then you disjoint union that with a bunch of copies of U, one for each non-identity element of mu n. So you can check directly, for example, that that's a representing object, and then, well, how many maps are there from X to that? There's only just the one section. And I'll talk a little bit. I mean, I'll give that as an example, kind of later today when I talk about kind of representability of certain sheaves. All right. Are there any questions? All right. So now I want to return to this issue that we had before, which is the independence of these groups of the compactification, and that's going to require some information about proper base change. So I guess for the next while, we're going to be talking about proper base change and finiteness results. So far, I mean, we actually really don't know that much. So we know the cohomology of curves, and that's pretty much it. But one important thing we know is that the cohomology of curves is kind of finite dimensional, right? So as long as you take the cohomology of, let's say, mu n, and you're over a field where the characteristic of the field doesn't define n, then one consequence of this computation is that all the groups you get are finitely generated Z mod and Z modules, right? So a natural question is how true is that in general? And at least part of proper base change is an answer to that question. So it says that in quite wide generality, cohomology of varieties has good finiteness properties, and even derived push forwards do. So okay, so let me kind of tell you what I mean by good finiteness properties. And so this is, if you'd like, this is an Étale cohomological analog of the coherence of proper push forwards in coherent cohomology. Right, which says that if you take the derived push forwards of a coherent sheaf through a proper morphism, you get coherent sheaves. All right, so here's the definition. So suppose we have F, which is a Étale sheaf on X. Oh, sorry, I'm using different notation here. A sheaf on X Étale, not necessarily a sheaf of abelian groups. This makes sense for sheaves of sets, and we say this is constructible if two conditions are satisfied. So what are these conditions? So one is a finiteness condition, and the other one is a kind of condition about the shape of the sheaf. So it's saying that at least it doesn't look too different from a locally constant sheaf. So what's the definition? So first of all, there's this condition on the shape. So for every I z to x, a closed embedding, maybe let me just write it that way, there exists a non-empty open U inside of Z such that when you pull back F to Z and then restrict to U, this is locally constant. Can anyone tell me what it means for a sheaf to be locally constant? Sorry, Jose, I missed some comments in the chat from what looks like quite a while ago. So yeah, so I've been calling X the compactification. And Arvind and I agree, this is neat. All right, so can anyone tell me what this local constancy means?
So there's some neighborhood where the restriction is constant sheaf.
So what do you mean by neighborhood, and what do you mean by
around each point there's a neighborhood such that the restriction of the sheaf is a constant sheaf?
Yeah, so let me yeah, so what does constant sheaf mean?
Just the sheafification of a, I guess in this case a fixed abelian group.
Yeah, great. Okay. Yeah, so what this means, as Sasha said, is that there exists some cover phi to U such that I star F restricted to V is constant, meaning the sheafification of a constant pre-sheaf. Great. Okay, and then B, the second condition is that the stalks of F are finite. Right. So let's just give an example. So if I have U into X is an open, then J lower shriek of, let's say, mu n is constructible. Can anyone explain to me why this is true? Okay, so what do we need to check? So first of all, we need to check that the stalks are finite. That's not too hard, right? Because the stalks are just either 0 or mu n. So how do we check that that this first condition? Can anyone suggest a way?
I think you can just use the intersection of u and z.
Right, exactly. So we have some z embedding in. If its intersection with u is not empty, we can just use the intersection with u, and then we get, well, not quite a constant sheaf, right? Mu n is actually not a constant sheaf, right? Because there's a Galois action on it. It's not the sheafification of an abelian group, but we can take the cover where we adjoin the nth roots of unity to the intersection of u, and that'll trivialize it. And then the other possibility is that z doesn't intersect u, it lands in the complement, but then you just get the 0 sheaf, which is indeed constant. All right, are there any questions about that example? All right, let me give you a more general example. So suppose that f is represented by a quasi-finite scheme. Okay, so let me draw a picture. So let me actually draw a picture. So here's a picture of J lower shriek mu n. This is what we had before. So here's this line is supposed to be x, and then inside of it we have this open u. So I described this verbally before, but I wanna actually kind of draw a picture of the representing object. So J lower shriek of mu n is represented by here. This is the identity over all of x. Maybe I'll actually call it. Well, yeah, I'll write it in multiplicative notation because it's mu n. Okay, and then over u, you just kind of get a copy of mu n. So this part is mu n. So you should check as an exercise that this actually represents J lower shriek of mu n. Is it clear what I mean by this picture? Does anyone have any questions about it? I'm trying to, yeah, if you want, I'm happy to rigorously write down the scheme I mean.
And so a section over some open would sort of have to extend into some part over beyond u, and that's why, for instance, there's no section over u over x. Right?
Yeah. So if you have an open which is not contained in u,
right, which is not,
like over here, for example, it has to land in 1, right? And then as long as your open is connected, then that forces its image to be contained in this one section 1. Right, which is why it must be 0. Yeah, so let's actually step back for a second and say, what is sheafification doing when you take J lower shriek? It's just saying that if you've an open which is not connected, then you evaluate on each component of it separately. Right. So for example, the sort of the situation where the formula for J lower shriek I wrote down won't be accurate is if you have an open which has one piece which is not contained in u and another one which is, right? So yeah, so what's happening, so in particular, if you have a connected open which is not contained in u, its image just has to land in 1. Does that answer your question, Arvind?
yeah, I think so. And also, is this sort of just a general picture of a constructible sheaf?
Yeah, so I'm about to state a theorem about that. Yeah, so here's a theorem which is this is some kind of characterization of constructible sheaves. So this is a hard theorem, which I'm not going to prove. So I'm going to let f from the big Étale set of x to the small étale site of X be the obvious morphism. So can anyone tell me what that supposedly obvious morphism is?
You include the Étale schemes the other way, the Étale covers the other way.
Yeah, exactly. So a map of sites is a functor going the other way, and if you have an Étale X scheme, that is an X scheme, and then you can just include it in. Great. So suppose I have this map, and I have a sheaf on the big Étale site. Sorry. Okay, F, which is a sheaf on the big Étale site. So such that two conditions hold. So one, F, there's a natural map from F to F upper star, F lower star, F. And you want this to be an isomorphism. And I'll say what this means in a second. And two, F lower star of F is constructible. So then the theorem is that F is represented by a quasi-finite X scheme. Okay, so let's say what this means. So first of all, what is F lower star of capital F? Can anyone just give me an explicit description of it?
Is that just
Is it like just the base things?
What do you mean by that?
Like you have a cover on. Oh, I see. To see actually.
Yeah.
So you look at
You can just
you evaluate the CIF as the base things, right?
Yeah. So that's the general definition. But if you had a map of schemes, but here we just have a map of sites, right? So push forward through map of sites is you have a functor going from right to left, and you given a sheaf here, it's the value of its push forward here is you go through the functor and then you evaluate. So can anyone concretely describe that? So here, this category is just a subcategory of this one, right? So a sheaf here is just a functor on this, and we're just restricting to the subcategory, right? That's what F lower star is. Does that? Yeah. So this is just the restriction, and then what is? Oh, sorry.
This is a good. Yes, it is. I see your
Okay.
point.
Yeah. So that's what this is. So it's a very concrete object, at least insofar as sheaves on sites go. And then what is this one saying? It's just saying that F is pulled back from the small Étale site. So in other words, this means that F is determined by its values on the small Étale site. Okay. So another way of saying this is just that if you have a constructible sheaf on the small Étale site, you can just make it. Any constructible sheaf on the small Étale site is representable, and moreover, the sheaf you get on the big Étale site just by pulling it back is representable. All right, so it's a stronger version of just saying that any constructible sheaf is representable. Does that sound plausible to y'all?
So just so I understand, this is saying that if you prescribe the values of the sheaf for like Étale, finite Étale covers.
Or maybe just Étale covers.
Or Étale covers, okay. Oh, because those are the objects in X little.
Yeah. So this condition one is just saying that F is determined by its values on Étale morphisms to X.
Okay.
Yeah, that's exactly.
And this implies that the push forward of F is also Étale representable?
So here, this is the push forward of F just means its restriction to the Étale site. So in particular, if you have something representable on the big Étale site, then it's yeah. I mean, okay. Let me just say a word like why am I writing it this way? It's because a quasi-finite X scheme is not in general in the small Étale site. So it's like this is a formal way of saying like what it means for a sheaf on the small Étale site to be representable, right? Like it's not literally representable on the small Étale site because the representing object is not in the category X little Étale, the little Étale site. It's in this bigger category.
Yeah, so that's what I meant. So you can't cheat like with the PPF thing and the torsos where you can actually make up an Étale scheme.
Yeah, exactly right.
Okay, thanks.
Yeah, so in general, the representing object is not Étale. Yeah, that's right. And I mean, okay, like maybe you want an example. Here's an example. Take any quasi-finite X scheme, which is not Étale, and then look at the functor it represents. All right. Well, okay. If you choose the wrong one, it might, that functor on the small Étale site might also be representable by an Étale X scheme, but in general. All right.
Can you give an example of an F for which this first condition is not true?
Sure. Yeah. So what's the easiest example? So if you take yeah. So take the sheaf omega 1. So that's like the Kähler differentials, right? So that associates to an X scheme T, the Kähler differentials on T. Okay. So in particular, that's a quasi-coherent sheaf. If you just look at smooth X schemes, let's say X is smooth also, just for simplicity. So if you just look at smooth X schemes, the rank, that's a vector bundle, and the rank of that vector bundle is the dimension of T, right? So in particular, that can't be pulled back from X because its dimension is jumping. Is that a good example, Arvin?
Yeah, I'm just thinking dimension of what, because I guess it's.
Oh yeah, so omega 1 is a coherent sheaf. So you can look at its, like on smooth things, it's a vector bundle, so you can look at its rank. But now if you have an object of X Étale that's a scheme T mapping to X, and you can compare that number to the dimension of the scheme. And my claim is that for smooth schemes, those things are equal. That's like it's like the cotangent bundle.
I see. Okay, I think that makes more sense.
Yeah. Yeah. So and this was discussed, I think, maybe on the Discord at some point. I think Nicholas asked some question about this kind of thing.
It wasn't me, but it was definitely discussed.
Okay, great. So yeah, so if someone scrolls back in the math chat, you'll see there was some discussion of this. All right, so now I want to state the first part of proper base change, which we can state now that we have this definition of constructibility. So suppose pi from X to S is a proper morphism. And F is a sheaf of abelian groups on the small Étale site of X. Then the theorem is that the derived push forwards of F are constructible for I at least 0. And moreover, we can compute their stalks. So Ri pi lower star F. Maybe let me use S bar. The stalk at a geometric point S bar of S is just the cohomology of the fiber over that point with coefficients in F restricted to the fiber. And this is true for all geometric points. S bar in S. Okay, so this is what I would consider to be the kind of important part of proper base change. We'll say the rest of it in a little bit, but I want to talk a little bit about what this actually is telling us. Are there any questions about the statement before I sort of dig into it?
just to make sure I understand the condition of the theorem. So F is just supposed to be constructible.
Yeah, that's right.
All right. Okay. Cool.
Yeah.
And actually, I'm more or less wondering about the direction of the the theorem, the hard theorem. In the first condition, the direction of the morphism is supposed to be from the right to the left. I mean, the natural homomorphism.
Let me think about that for a second. So we're taking the cohomology of the fiber to the fiber of the cohomology.
I mean the last theorem. Sorry.
Sorry, this one?
Yeah.
I think I wrote it in the right direction here.
Okay.
I think it goes from left to right. Because what am I using? I'm using that upper star.
I think upper star is a left adjoint, so it should be on the left.
I'm sorry?
I think he's right. I think the.
Oh, you think the map goes the other way?
So the map should go the other way.
Let me just check for a
adjoint.
second. Yeah, you're right. Okay. Yeah, you're right. Sorry about that. Yeah, thank you.
Thank you.
Yeah, great. And here the map goes, let's see, cohomology of the fiber or fiber of the cohomology. I think it goes left to right. Yeah, that's right. Cool. All right. Are there any questions about this? All right, so let me just kind of make some corollaries explicit. So suppose X is proper over a separably closed field. So I'm going to take S to be just spec of K, and suppose F is constructible. It's constructible. Then one, we have the cohomology of X Étale with coefficients in F is finite. And B, so it's sort of independent of base change along separately closed fields. So if K inside of L is an extension of separately closed fields, and there's a natural map, HI X Étale F to HI X base change to L Étale F base change to XL Étale. And this is an isomorphism. All right, so can anyone help me deduce the corollary from the theorem? So A is hopefully not too bad. Does anyone see how to do A?
The stalks of that thing are supposed to be finite, of all the derived push forward.
Yeah, exactly.
That's
So
exactly
this just follows from, so a constructible sheaf on spec K is just a constant. Well, if K is separately closed, it's just a constant group. And it has to be finite by constructibility. So that's A. What about B? Anyone? So if you'd like, we can think of this group as the stalk of Ri pi lower star F along our map like spec L to spec K. Okay, but now we're taking the stock of a constant sheaf, right? And that's just a constant group. So in particular, we're trying to compare these groups for different geometric points S bar of spec K. But that's just taking the stock of this constant sheaf on spec K. All right. Was that clear? Do you guys want me to say more about that?
Can you, for instance, give an interpretation of like an element of H1 of X S bar F restricted to?
I mean, so what it like what this is saying?
Yeah,
So this is saying like you have a map X to S. This is just saying take the cohomology of a fiber. So another way of saying this is that the stalks of the cohomology are the cohomologies of the fibers. So for example, if you have a map of curves, a map of let's say smooth proper curves over some base, what's this thing is, well, this cohomology sheaf is some a priori pretty complicated thing on the base. It's not easy to compute these things. Like we know they're the sheafifications of some pre-sheaf of cohomologies, but that's not something you can really work with. But this is saying that if you take the stock of that sheaf, it's just the same as taking your fiber, which is just a smooth proper curve, and computing its cohomology.
Oh, so it's like taking derived functors on the sheaf level, you get stocks that are the derived functors, I guess.
Yeah, exactly. Yeah. So the way I say this is stock of the cohomology sheaf is cohomology of the fiber.
Oh, okay. Oh, that's cool.
Yeah, and this is really something special about proper morphisms. Okay, so let's actually show that. So let's give kind of a non-example. So I want to show you that some kind of properness is necessary. So can anyone give me an example of a scheme and a constructible sheaf on it whose cohomology is not finite? So by the theorem, the scheme had better not be proper.
You have like A1 in the sheaf FP.
Yeah, so take A1 over, let's say, FP bar, and take F to be the constant sheaf Z mod PZ. And we computed this earlier in the course using the Arden-Schreier F sequence. So we showed that H1 of X Étale Z mod PZ is infinite. Great. Okay, so now let me state what people often state as the proper base change theorems. This is a corollary of the theorem above. Yeah, so what's the statement? So suppose we have a diagram as follows. So we have X to S, so map pi, and we have map T to S, and we take X prime is the base change. So this is a Cartesian diagram. I'm going to call this F prime and this pi prime. Then for any F, a sheaf of abelian groups on X Étale, there's a natural map F upper star of Ri pi lower star of F to, so this is what is this? So this is we push forward and then pull back to T. So the other thing we could do is pull back and then push forward. And this maps to Ri pi prime lower star of F prime upper star of F. Okay, so there's a map like this, and the theorem is that if pi is proper and F is torsion, then this map is an isomorphism. All right, so let's talk about this a little bit. So I claim that if T is just a point, or geometric point of S, this is just the statement from above. It's this isomorphism. Can anyone tell me why that is? Maybe let me scroll up so you can see both. Or you can't see both. Can anyone tell me why that is?
The upper star is just taking the stock, and the right is just the cohomology.
Yeah, so this is taking the stock of the cohomology sheaf. This is taking the cohomology of the fiber. That's exactly right. All right, so I will say one word about how to deduce this from the previous theorem, and then I think we'll be out of time. So the proof is that you construct this map using adjointness. So doing that requires some friendliness with derived categories that I don't want to assume in this class, so I'm not going to do it. But then once you've constructed the map, you can just check on stalks. And then the check on stalks becomes, modulo one issue I'll mention in a sec, becomes just the previous theorem. Okay, so what's the issue? So this works for constructible sheaves. But the theorem is stated for torsion sheaves, so there's some kind of devisage to get to that case. All right, so I'm out of time, so I'm not going to prove. So this theorem here, which is the kind of important part of proper base change, I'm not going to prove in detail, but next time I do want to say a little bit about it because it's extremely important. But maybe it's best to stop now since I only have 2 minutes left and pause to see if there are any questions. So next time I'll say a bit about the proof of this theorem, and then deduce a bunch of consequences, for example, the independence of compactification of compactly supported cohomology. So, are there any questions?
For this last remark, is it enough to use this remark that, I mean, as long as X or S isn't too horrible, then constructible sheaves compactly generate the derived category, or do you need something more?
What derived category?
Well, for elliptic sheaves? Oh, okay, I guess. Okay, I guess that's true.
Yeah, so I don't.
Okay, I guess.
Yeah, I think, I mean, you need something like that. I think what you need to do is you need to write torsion sheaves as maybe a direct limit of constructible sheaves.
Ah, there you go. Okay. Yeah.
I would have to think about what the exact statement is. I don't know off the top of my head.
Wait, so it is true that any torsion sheaf is the direct limit of constructible sheaf?
Don't quote me there. I need to check. Sorry. Yeah, I have to say I have never thought in any serious way about a torsion sheaf which is not constructible. So, yeah. Any other questions? All right. Well, we're out of time. I'll stick around for a few more minutes, but I will stop recording now.